Assalamualaikum warahmatullahi wabarakatuh. Welcome to our presentation slide of sound sensor dataset in IoT application. My name is Muhammad Ridwan bin Muhammad Nasaran, and my partner team is Siti Aina Najwa binti Muhammad Ridwan. So our today's agenda is we will discuss about the introduction, the objective of this project, the methodology, the results, and also the conclusion of this project.
This project showed that sound sensor data can be used to detect unusual behavior in IoT systems, even without complex hardware. Using acoustic signals from the IoT set dataset, we applied basic machine learning techniques like regression and decision trees to spot patterns in MQTT and TCP communication. We found that even a small number of features such as message types and payload sizes can reveal useful trends. For example, larger MQTT messages often match larger TCP segments. The system also worked well with the Thingsboard platform, allowing real-time monitoring and fast detection. Overall, this proves that lightweight audio-based data paired with simple analytics can offer a scalable and cost-effective solution for intrusion detection in smart environments. There are a few objectives of our project. First, explore the potential of sound sensor data in detecting anomalies within IoT communication. Second, to analyze TCP and MQTT protocol features. Third, to apply lightweight statistical techniques like correlation and regression to model normal traffic patterns. Fourth, to assess feasibility of intrusion detection in the absence of label attack data. And lastly, to visualize and interpret network patterns using graphs to support anomaly detection in resource-constrained systems. I will explain about this flowchart. First, we begin with data acquisition. This is where sensor readings are collected, including sound signals and protocol metrics like MQTT and TCP. Next, we pre-process the data. This involves cleaning noise, formatting fields, and ensuring everything is ready for analysis. Then we label the dataset. If attack labels exist, we apply them. Otherwise, we prepare for unsupervised analysis or rule-based tagging. After that, we aggregate the features. Here we group relevant sensor and protocol values for training, like ting message length, flags, and sequence numbers. The system proceeds to model training. We train machine learning models to learn behavioral patterns that might indicate normal or abnormal activity. At this decision point, the system checks, is there any sign of intrusion? If no, the system loops to continue monitoring. And if yes, it triggers alerts and possibly automated defensive actions. This flowchart shows how each part of our system contributes to real-time intrusion detection, from collecting sound sensor data to making security decisions. It's designed to be lightweight, adaptive, and suitable for resource-constrained IoT setups.
You can see the figure number 1. This is the code to connect the Google Colab session to Google Drive at the path content slash drive. This is the drive that I save, and then this is to allow us to access and use files stored in our drive directly from Colab. And then the second figure, the second coding that you see in the slide is to define a variable named dataset path and assign it the file path to a CSV file, which is stored in Google Drive. This path points to a file called IoT sound sensor.csv, located within the folder structure my drive ECE523 under the user's Google Drive. So by storing this path in a variable, the file can later be accessed easily in the notebook. You can see the figure number 1. This is the code to connect the Google Colab session to Google Drive at the path content slash drive. This is the drive that I save, and then this is to allow us to access and use files stored in our drive directly from Colab. And then the second figure, the second coding that you see in the slide is to define a variable named dataset path and assign it the file path to a CSV file, which is stored in Google Drive. This path points to a file called IoT sound sensor.csv, located within the folder structure my drive /ECE523 under the user's Google Drive. So by storing this path in a variable, the file can later be accessed easily in the notebook. And then for the figure number 5, this code loops through each row of data frame SF, converts selected TCP and MQTT fields into integers, package them into a dictionary named data, and then sends that data as JSON on a Thingsboard server providing a measure of reliability for each variable's mean estimate.
This descriptive analysis summarizes the behavior of both TCP and MQTT traffic observed in our dataset. We can see the average TCP segment length is around 10.77 bytes, while MQTT messages average around 9.54 bytes. The high standard deviation in TCP.sequence and MQTT topic_len indicates variability, especially in sequence numbers and topic naming. Skewness and kurtosis help us understand the distribution. Most features are moderately skewed, hinting at occasionally spikes or sparse values. This analysis helps us identify which features are stable and which might signal abnormal behavior when they fluctuate. This correlation matrix helps us understand how different MQTT and TCP features behave together. Identifying strong correlations allows us to choose meaningful features for modeling. MQTT-len and TCP-len show a correlation of 0.9993, meaning larger MQTT messages tend to generate larger TCP segments. TCP sequence and TCP-ACK show 0.8383, indicating synchronized packet flow. MQTT conflict cleanness has a negative 0.6138 correlation with TCP-ACK, suggesting session reset behavior might reduce acknowledgement traffic. MQTT message type has moderate positive correlation with TCP topic-len and MQTT-len, suggesting more complex message use longer topics. These insights help guide our regression modeling and anomaly detection, choosing features that reflect real behavior structure.
Alright, so now we move to the Thingsboard analytic. Alright, so as you can see in this slide, this is the result that we get from the Thingsboard based on our sound sensor data. So as you can see, the bar chart further highlights the comparative frequency of each feature, reinforcing that TCP-len and MQTT-len are the top contributors among the 35 total data entries. This visualization aids in quickly identifying which features are more active or heavily reported in the telemetry stream. The radar chart complements this by showing the relative coverage of each feature, mapping how they vary in scale across the network protocol stack. Features like MQTT's ver, which is the variable, and TCP.ACK appear with moderate frequency, while MQTT.topic-len shows no activity, which may indicate a limitation or omission in the data set. And then the third one is the state chart, offers a real-time view of the data transmission and behavioral states of each feature. It confirms that TCP.len and MQTT.len and a few others remain consistently on during the transmission interval, implying they are persistently involved in the network's operation. The state persistence may be useful for real-time monitoring and alert system in the IoT application. Alright, so for the pie chart and donut chart, both emphasize the dominant roles of TCP LAN, which is 41%, and MQTT.LAN, which is 35%, indicating that packet lengths are the most prominent metrics in the dataset. These attributes are key to identifying traffic size anomalies, which often serve as early indicators of intrusion attempts. Less frequent features such as you can see in the chart, which is the MQTT message type at TCP flags.ack and the TCP.sequence, still contribute to the dataset's diversity and may reflect more subtle behavioral patterns. So for the alarm panels display, two critical triggered by the edge IoT cybersecurity system on the created time, as you can see. So both alerts are marked with active status and remain unacknowledged, indicating that immediate attention is required to prevent potential system compromise or hardware damage. So the first alert is related to high frequency megahertz, which may signal abnormal or malicious communication activity in the wireless transmission layer, potentially from unauthorized access attempts, signal jamming, or frequency-based DOS, which is the denial of service attacks. And then the second one is the alert concern high temperature, which could point to overheating of IoT device or infrastructure. This situation can be caused by overloading, prolonged usage, environmental factors, or malicious firmware manipulation, all of which can impair device reliability and cybersecurity. Both alarm are assigned to my name, suggesting that he is the designated system administrator or analyst responsible for addressing this issue.
Today's fast-moving digital world, the Internet of Things IoT is everywhere, from homes to industries. But with more connected devices, we also face more security risks. This project looks at how sound sensor data can be used to detect intrusions in IoT systems, even when resources like bandwidth and power are limited. We used a portion of the Edge IoT set dataset to focus on audio-based traffic and protocol features like TCP and MQTT. Even with just 13 data samples, we found interesting patterns like how large MQTT messages often match larger TCP packets. Through correlation analysis, regression graphs, and visualizations, we showed how protocol behavior can reveal network trends. By applying simple yet effective statistical techniques, our study shows that lightweight sensor data, especially sound-based telemetry, can help IoT systems monitor communication and spot potential threats. The results offer a flexible and low-cost way to enhance IoT cybersecurity.